Let's go through LeetCode 1110, delete nodes and return forest. For this question, it gives us a tree nodes root and also an integer array to delete. And let's delete those kind of nodes which have the value in the to delete array and return a list of tree nodes. And it says that those kind of values are distinct. Let's look at the example. This root 1, 2, 3 has a value 1, 2, 3, 4, 5, 6, 7. And we need to delete 3 and 5. So if we delete 3, right? Then what we do is that we need to set this one's right child to be none. And also we need to add 6 and 7 as a tree node to our result. And the 5 is deleted. So let's see on this tree there is no 5 node. So intuitively we're thinking about that we should do something like a divide conquer, right? So we can have a global result of these tree nodes. And for a tree, if its left child has called uh, we call the divide conquer for the DFS function, so has been called this DFS function, then means its left child has been processed. And if its right child has called the DFS function, means its right child has been processed. So um, then we need to check a current node to check whether it need to be deleted. So if it does not need to delete, right? We don't need to add current nodes to, we don't need to, there is nothing to do with the result. We don't need to add anything, right? But the thing is that for current node, we should determine whether we should set its left child to be none or not, determined by whether the left child itself has been deleted or not. For example, if we have um, for example, if we have um, for example, we want to delete for example, we want to delete 2, right? Let's just use this example, delete 3, right? Because 3 is deleted, so what we need is that for current node, its right should set as none, right? So this is one thing is even current node doesn't need to delete, but if its right has been or left has been deleted, we should set its right or left to be none. Um, so if current nodes, for example, should be deleted, right? So what we need to do is that we need to check if its left child has been deleted or not. If it's not deleted, we need to add its left child to the list of results. If its right child has not been deleted, we also need to add its right child to delete it, right? So how do we know if a node is deleted or not? Um, for this question, we can have the DFS, the divide conquer, return a result, which is the tree node, right? So if a node is deleted, we return none. And if that node is not deleted, we just return this node. So in that case, we'll say if its left DFS result is not null, we need to add the left nodes to our result. The same thing to the right nodes, right? If the not null, we add that to our result. So this will be our solution, right? And for example, this is, for example, 3 has need to delete. For example, 6 has need to delete, right? Do we need to care about the 6 children, right? We don't need it. For example, we already have 8, right? Because when we DFS to 6, those kind of 8 already added to our result. So even with 3, 6 don't need to add, but those kind of subtraits have all been processed. So let's just write code for this. In order to have O1 operation to check whether this node need to be deleted, we can change this to be set. We call delete set. So what is this for int d to delete? Have a delete set add d, right? So we're going to have a list of tree node result equals new array list. Okay. And we know this DFS need to return result, so we're going to have a tree node result equals DFS root delete set and the result, right? So the things that for current node, if it's not being deleted, we still need for the root, right? We still need to add to the result because we didn't add this result until we passing to its parents, right? So we should still check if result is equal to none. We are going to have result should add this kind of root, right? Then return result. And our DFS we should have a return result. So we're going to have a tree node, button node, set integer, d set, and a list of tree node as a result. Right? So what we do is that first, if this node equals to none, right, we just need to return none. Then we'll have node dot left equals DFS node dot left delete set and the result, right? So we do this one because if it's left has been deleted, it's null, right? We just need to set current left to null. If it's still return it's node left, right? So this code just didn't do anything, right? Then node dot right equals I mean, but DFS still calls, right? Process is left. If return nodes dot left, so there is no cutting, right? If it is not, just like we cut the left tree, set it as null. Node dot right equals DFS node dot right. They are set the result, right? Then we'll say if for this kind of deleted set contains node dot value, right? That means current node should be deleted. So for this case, we need to return none, right? If not, what we need to return current node, right? So if contains, right? Contains, as we mentioned, right? So 3 need to be deleted, but whether 6 need to be added to our result determined by whether 6 is deleted or not, right? So how can we determine if 6 is deleted? Is this result the line 33, whether it is written now or not, right? So we'll say if node dot left done equal to null, we just have result add node dot left. And we'll say if node dot right done equal to null, right? We have result add node dot right. So this will be the code. So let's say there are n tree node and there are m deleted integers. So this will be the set convert to this will be OM, right? And for this DFS travel, suppose that every node is traversed once, so that is ON. So that will be ON plus M time complexity in the space, right? So this will be OM. And this one is ON, right? So it will also be OM plus N space complexity. And the Python code is very similar. We are going to have delete set equals set to delete, right? And the result equals this. We are going to define our DFS. So what we are going to pass into node should be optional. To node. And yeah, we don't need to pass a result. We just put this one as a variable outside. And let's have return an optional node. Then we'll see if not node, just return none. And then we're going to have node dot left equals DFS node dot left. So this line has did two things. One is process its left child. And also, if left it returns null, means the left child has been deleted. So we'll set a current node its left to be null. Node dot right equals DFS node dot right. So what we do is that if node dot value in delete set, right? Then we're going to, if node dot left is not null, we need to add a result append node dot left. And if node dot right is not null, we should have result append node dot right? And because current node is deleted, we should return null, right? And if not in delete set, we should return node. So in our main function, what we do is that we're going to have R equals DFS root, right? So if R, we should have a result append R, right? And in the end, just return result.